therefore, while calculating the probability distribution, a single electron passes through both the slits at once. That no one understands. That how does this electron pass through both the slits at once? So, electron is described by a wave function, which is here and here. If I make a measurement by putting a microscope there, then it will be found either here or there. But if I do not make that measurement, and this is very beautifully explained in the Feynman lectures, the electron passes through both the slits, interferes with itself to produce a probability distribution, which is the same as the intensity distribution given by the classical optics. So, as I told you, the mass of the electron is known. How does the electron pass through both the slits? So I do this double hole experiment or double slit experiment with the electron gun. And the electron gun, it sends out electron, passes through both the slits, you think if it is a particle, it will pass through either hole number 1 or hole number 2. So if hole number 2 is closed, you get this intensity distribution. If hole number 1 is closed, you get this intensity distribution. So naively you say that if both holes are open, an electron has a very well-defined mass, very well-defined charge, it has to pass through either hole number 1 or hole number 2. So you should expect an intensity distribution like this. But what you observe is the interference pattern. And that can only be explained if a single electron passes through both the holes at once. How does it pass through? One does not know. So this is the build-up of the interference pattern. I'm sorry, this caption went off. This is with 10 spots. So when you make a measurement, the electron will collapse at a point. Which point it will collapse, no one can say. But when you make a measurement with millions of electrons, slowly the interference pattern will evolve. This experiment with single electrons is considered as the most beautiful experiment in physics. Similarly, for a photograph showing of a young lady, that you have this with 3,000 spots, 3,000 photons, 28 million spots with 28 million photons. Where will an individual photon or electron will land up? I do not know. I can only predict the probability distribution. So in that sense, the most fundamental theory now available is probabilistic in form and not deterministic. So let me skip this. So I have a single photon source. One by one electron comes in. It gets reflected and transmitted. So you will say, normally people will say that if there are 1,000 photons coming, 500 will come here, 500 will go there. That is an incorrect answer. A single photon is here as well as here. It is reflected and transmitted. So I consider this experiment with a polarization beam splitter, which splits into two orthogonal polarized beams. So I consider a sodium lamp polarized, 45-degree polarized photons. This polarizes at 45-degree polarized. So it will have both S polarized and half the intensity goes here, half the intensity goes here. Then you do with a single photon source and you block this beam. Then the reflected beam is always S polarized. On the other hand, the transmitted beam is always P polarized. But if you have a single photon source and if both arms are open, and if they are carefully managed, then the photon is here as well as there. It is in a superposed state. It superposes with itself to produce a 45-degree polarized beam. This particular diagram I have taken from a book by Zillinger. So the photon is here as well as here until I make a measurement. If I make a measurement, then it is either here or there. So let me consider 10 more minutes. In double refraction in calcite. As you all know, calcite has a. So when an unpolarized light beam is incident on normally on a calcite crystal, it usually splits up into two linearly polarized beams. So I have a 45 degrees. So this is a calcite crystal. And let us suppose this is X polarized, this is Y polarized. So I will call this as XY device. And I can rotate that. And the two beams that will come out will be U polarized and V polarized. The propagation is in the Z direction. So I can rotate this XY device to produce this UV device. I can also rotate it to produce a sigma eta device. All these axes are at right angles to the Z axis, which is the. So I now have a calcium 40 atom, which emits two photons of different frequencies. And as most of you would know, if it is passed through an XY device, if I observe an X polarized photon, then I don't have to measure the second photon. It will automatically collapse to a Y polarized beam. The two photons are said to be entangled. According to quantum theory, the polarization of the photon traveling to the left or to the right is not known before one of them is measured. Similarly, for those who are familiar with, have done a course on quantum mechanics and done the Stern-Gerlach experiment, you have how do I visualize the electron? It has a magnetic moment. Let us suppose I take a silver atom and pass through an homogeneous band. This is the famous Stern-Gerlach experiment. You get the Z up state and Z down state. And then I pass through the Z up state particles, where I know for sure that the spin is pointing upwards, to a inhomogeneous magnetic field in the X direction. The Z up state is a linear combination of X up and X down state through the solutions of the Pauli spin matrices. And so therefore, there's a half probability of getting X up and half probability of getting X down. Whether I will obtain the spot here or here, I cannot predict. No one can predict. And if you have assume two spin particles in the singlet state, then it is a superposition of up, down, and down, up. And if so, if one of them is passed through a Stern-Gerlach apparatus in the Z direction, and if I find this to be Z up state, then automatically the second particle will collapse to a Z down state. If I pass this, these two particles are entangled. And if I pass through the X, a Stern-Gerlach device in this X direction, if it collapses to a X up state, then this will collapse to a X down state. I don't have to measure that. So I come back to the light experiment. I have two photons coming in opposite direction. If one collapses in the X direction, the other will collapse at the Y. So if the photon going to the left is passed through an XY device and it is found to be X polarized, then the photon going to the right collapses to a state in which its polarization state is Y polarized. And I don't have to measure that. These are known as Alice and Bob's famous experiments, as I'm sure all of you know. Similarly, if I rotate this, if the photon going to the left is passed through the UV device and it is found to be U polarized, then the polarization of the photon going to the right collapses to a state in which its polarization state is for sure B polarized. So this is the collapse of the wave function is unique to quantum mechanics. Whatever happened to one particle would thus immediately affect the other particle, wherever in the universe it may be. Einstein called this spooky action at a distance. So in 1935, as all of you would know, EPR, Einstein, Podolsky, and Rosen, Einstein was at that time in Princeton, wrote a very beautiful paper, and in which he writes, if quantum theory, read this carefully, if quantum theory was correct, then two particles, which are millions of kilometers apart, millions of kilometers apart, can be entangled in the sense that by determining a property of one of the particles, the property of the second particle can be instantaneously changed. And special theory of relativity forbids the transmission of a signal faster than speed of light. This came to be known as the famous EPR paradox. About 30 years later, experiments confirmed the predictions of quantum mechanics. Namely, Einstein's impossible proposition was in fact correct. Instantaneous changes in widely separated systems did occur. EPR argued that if, without in any way disturbing a system, because it is millions of kilometers away, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, like the polarization state, then the second particle must have possessed the measured property before the measurement was carried out. So this is the concept of hidden variables. So we assume that the photon must carry all the information. Thus, there must exist hidden variables so that we can assign values of all observable systems. So if one photon is characterized by XU sigma, that means if it is passed through an XY device, it will be X polarized. UV polarized, then it is U polarized. Sigma eta device, it will be sigma polarized. If I ascribe a particle, then the second particle will be at right angles to that. Similarly, if I write this as YV sigma, then the second particle will be XU eta. And there can be, with three such orientations of these devices, I can have 8 possible cases. XU sigma, XU eta, XV sigma, XV eta, YU sigma, YU eta, YV sigma, and YV eta. There are only 8 possible, and corresponding to this XU sigma is Y, the second particle will be YV eta. So let there will be N1 pairs like this, N2 pairs like this, N3 pairs like this, and there are 8 possibilities. So in the third and the fourth, the left is X and the right is U. So P of XU is the probability that if the left-hand photon is passed through an XY device and you measure it X polarized, and the right-hand device, if you pass through an UV device and it is measured, it measures U device, then the probability of that will be N3 plus N4 divided by, because only in these two cases, the left is X, the right is U. Similarly, you can write left is X, right is sigma. Similarly, sigma and U. So I have, you have to do this little, it's very simple. P of X sigma and P of sigma U, you add them together, you get this. And then you have P of X U equal. So this includes N3 plus N4. So this quantity must be less than, this quantity must be less than that. And this is a simple form of Bell's inequality. So according to quantum theory, now look at this. According to quantum theory, what is P of XU? That is, I pass through a XY, the left is XY device. So I know that it is the X polarized. Then quantum theory says it will be Y polarized. And so the probability for measuring it U polarized according to the law of Malus will be cos 90 plus theta whole square. That is sine square theta. So Bell's inequality says that P of X comma U is half sine square theta. P of X comma sigma is half sine square phi. Simple application of law of Malus, and P of sigma U is equal to so much. So thus, according to quantum theory, this inequality assumes hidden variables. But if quantum theory I assume, then Bell's inequality will imply that sine square theta must be equal to sine square phi plus this. If we assume theta is equal to 2 phi, then this will mean sine square 2 phi is less than 2 square phi. For phi equal to pi by 6, this will imply this, and this is impossibility. So this result is by applying quantum mechanics to this inequality. And therefore, thus quantum theory and Bell's inequality are not compatible, which implies that either quantum theory is right or theory based on hidden variables, but not both. So there are a large number of experiments that have been carried out. This is the experiment by Alan Aspect. I don't know whether it is silent, yes or not. An apparatus for performing a Bell test. A source emits pair of entangled photons of different frequencies, nu1 and nu2. Their polarizations are analyzed by polarizers. These are the XY or UV devices. And Aspect writes, the linear polarization correlation of pairs of photons emitted in a radiative cascade of calcium has been measured. The new experimental scheme using two-channel polarizers is a straightforward transposition of EPR thought experiment. Gedanken is thought experiment. The present results, in excellent agreement with the quantum mechanical predictions, lead to the greatest violation of Bell's inequalities ever achieved. Zeilinger writes that Bell's theorem represents as one of the most profound discoveries since Copernicus. Bell delivered a death blow to the local realistic picture of the world. Many experiments have demonstrated, as does Alan Aspect's experiment, that the predictions of quantum mechanics for entangled particles are fully correct, and the world is really as crazy as predicted by quantum mechanics. So coming back to Feynman, famous messenger lecture at Cornell, electrons do not behave just like particles. They do not behave just like waves. Electrons in orbit are not somewhat like a cloud or fog of some sort surrounding the nucleus. It behaves like nothing that you have seen before. Well, there is one simplification. Electrons behave exactly the same way as photons or protons or neutrons. So they are both. So I think I can safely say that nobody understands quantum mechanics by this. I think he implied quantum mechanics is just the solution of the second order differential equation. And if you do not have the capability of solving it exactly, you can use approximate methods or numerical methods to solve it. What one does not understand, so quantum mechanics is not that difficult. But it is one of the most successful theories. What one does not understand is how can the electron pass through both the holes? That is a very difficult question to answer. So these are the references, the three most beautiful books on quantum mechanics. And if you go through them, I'm sure most of you have gone through them. Each one has his own way of introducing quantum mechanics. You read Dirac's book or Feynman lectures or David Bohm's. They are three great authorities. What I have done today, and all the diagrams that I have given is given in the 7th edition of my optics book. So I end up with quoting Einstein. He wrote in 1917, just after discovering the stimulated emission. For the rest of my life, I will reflect on what light is. I will study and try to find out what light is. And then 4 years before his death, he wrote, all the 50 years of conscious brooding have brought me no close to the answer to the question, what are light quanta? Of course, today every rascal thinks he knows the answer, but he is deluding himself. So I am an old storyteller. I do not know what the truth may be. I tell you the tale as it was said to me, Sir Walter Scott, in The Lay of the Last Minstrel. Thank you. I hope I have not exceeded my time too much, Professor Panigiri. Thank you.
Thank you, Professor Ghatak, for a wonderful lecture. Very informative as well as lucid, particularly for the students of not only physics, but students of all subjects, I must say. So it was really wonderful because quantum mechanics has been such a romantic subject, actually. According to me, it has attracted so many people. I think very nice to think about particularly Einstein's own contribution and Einstein's contributing to the debate of quantum mechanics has been one of the most wonderful things. Schrodinger, Heisenberg versus Einstein.
Yes.
So I'm very happy that you have brought out the spirit of quantum mechanics. I think we'll take some questions now. Is it okay?
Okay.
Yeah, it is okay. Yeah.
Can we take some questions?
Simple questions. Simple questions.
Well, I think most of them are simple questions, I'm sure. So, yeah, there are several questions in the chat box, but there
Okay,
is
let me see the chat box. Let me see the chat.
You can see the chat
I'm
box.
interested in the derivation of Bell's inequality explained here. So, if you read a book by Townsend and my own book on optics, I have given this derivation there, and so it is given there in detail. But I have given all the steps here. I have given all the steps here. So I hope you can see that. Let me see.
Somebody knows the book name, I think. Balasubramaniam Soundarya writes, he's a great fan of your book. So,
so the book is both my optics book and our quantum mechanics book with Professor Loknathan has this derivation, the
great.
latest edition. Yeah,
so another person writes, feeling really great fan of his books.
Oh my God.
Devajyoti Datta, this is the best book for my BSc course.
Oh my God.
Right.
Someone writes, can electron also be called as an electromagnetic wave? Oh, no. Shubham Das. Can electron also be called as an... No. Electron and a photon are two different quantities. And electron is approximately described by the non-relativistic Schrodinger equation. And you describe the electron as I understand it. You see, why do I have so many quotations of Feynman? I have so many quotations of Feynman because if I wrote that no one understands quantum mechanics, then you will not believe me. But if Richard Feynman writes that no one, then you will say, oh, if Feynman writes, then. But it is true that what is an electron, what is a proton? If it is really a particle of a definite mass, then how can it go through two holes at once? This no one understands. So certainly, answer to your question, you don't confuse between electron and an electromagnetic wave. If you quantize the electromagnetic wave, you will get the concept of the photons, and electrons are described by a localized wave packet, and inherent with that wave packet is the uncertainty principle. So everything is contained in the solution of the Schrodinger equation. And Schrodinger equation, if you take this singlet state, that example I have not discussed in my optics book, is very important. You take a singlet state of two spin half particles. You see, how do you visualize the spin half particle? I visualize this is my perception, that electron is ascribed a certain magnetic moment. So I visualize the electron as a tiny magnet. And I want to make a measurement of the Z component of the magnetic moment. So I pass through a Stern-Gerlach apparatus, which has an inhomogeneous magnetic field in the Z direction. And it is either Z up or Z down. Either Z up. And now I take this Z up beam to another X up apparatus. And then I extend the analysis. This is a very beautiful experiment to a singlet state, two particles forming a singlet state. Total spin is 0. And there are particles like that. And so two spin half particles detach themselves like the two photons. And if one is spin up, then the other is spin down. If one is spin X, then the other is X down, and so on.
Yeah, there are various questions. Kamal is right. Another, you can see that.
Well, let's end here.
I can read. Komal is having a question, very stupid questions he writes. From childhood, that light does not have mind or something like that, then how it knows to take least time or using principle of diffraction?
The Fermat's principle can be derived from Maxwell's equations. So Maxwell's equations cannot be derived. So Fermat's principle, the principle of least time, is follows from Maxwell's equations. So you see, this is the thing. The Newton's laws of motion cannot be derived. Maxwell's equations cannot be derived. They are laws. The entire book, the book on electricity, classical electricity and magnetism, is not nothing less or more than solutions of Maxwell's equations under different boundary conditions. So something like that. So
And Rahul Garg, he writes how Galileo created the environment of zero gravity at the Leaning Tower of Pisa.
oh no, what Galileo did was that Aristotle had that a heavy ball will fall faster, because if I have a feather, it takes a longer time to drop. What Galileo said was, and Newton's laws were not discovered. What Galileo said was that the two balls, heavy and light, will take the same amount of time, and that he demonstrated. He went up on this thing, and on the Tower of Pisa, he dropped two balls, and he showed that the two balls take the same amount of time. There is now, if you go to YouTube, there is a gentleman by the name of Brian Cox, who has done this video, that he has taken a very heavy lead ball and a feather in an evacuated chamber, and he drops a ball, a heavy lead ball and a feather. Both take the same amount of time in free space. So this experiment has been carried out by going to the surface of the moon, and people have shown that both the hammer and
somebody write Dropat Umesh, is changing electromagnetic field actually causing magnetic field and vice versa? If so, why don't we take into account the cause effect delay when you have partial pictorially represented electromagnetic wave? So you can see.
I understand is the following, that if I have Maxwell's equations tell us that if I have a changing electric field, it will cause a changing magnetic field, and a changing magnetic field will create a changing electric field. That is how the fields propagate in space, in vacuum, and that is how the fields. So you see, you put a charge. That is the importance of the concept of the field. You put a charge here, and then it produces a field in the entire space surrounding it. Let us suppose it is placed in vacuum. So it produces a field. And if you make the charge move up and down, the field also moves up and down. When the electric field moves up and down, then it generates a magnetic field. And the magnetic field generates an electric. That is how the fields propagate.
So Prachiti Athalia, right, is Schrodinger equation is an empirical formula. So
no, there is a certain amount of, you see, that is why I gave a heuristic derivation of that.
Yeah.
If you read 1926 paper of Schrodinger, then there is a justification of that, but it is not rigorous. That is, it is not an empirical formula. It is not. There is a loose arguments leading to that. Loose arguments related to wave-particle duality, which gives you the Schrodinger equation. But it cannot. You cannot have a rigorous derivation. You can never have a rigorous derivation of the Schrodinger equation.
Yeah. Well, as
I said in my last line, I do not know what the truth may be. I tell you the tale as it was told to me.
I mean, just to clarify, sometimes I say it's a part of the postulate. It's an eigenvalue equation, gives a stationary state. That's it. You live with that.
A postulate, that is what Feynman also said.
I mean, the time-independent part of the Schrodinger equation, not the time-dependent. That is a postulate.
No, time-dependent. No. Correct is the time-dependent. Time-dependent Schrodinger equation. You can say that it's a postulate. Maybe you can. It's a postulate. That's what. Just a clarification.
Yes. Then Ajoy Samuel writes, if light is neither a wave nor a matter, then what is it? It hurts my brain.
I don't know. I don't know. That is the not that I do not know. No one knows. I don't know what is an electron. How that electron passes through both the holes. That no one knows. And
So
now you have experiments with neutrons, with protons, with all those particles. So that's what Feynman says, that the good thing is that electrons, protons, neutrons, photons, they all behave in the same screwy way. That's what
so
uh,
Shruti
I
Sharma,
would
right?
advise. I would advise all. I'm sure most of you have done that. To listen to you go to YouTube, write down Feynman's messenger lecture on probability and uncertainty, and you will get this 1964 messenger lecture of Feynman. It is one of the most he gave 6 lectures, out of which 2 stand out. I mean, they are just too beautiful. One on gravitation and one on probability and uncertainty. So most of the things that I have said today are given there. I will urge all students to go there. I will also tell you one more thing, that as Professor Paul had mentioned, I had the privilege of doing my PhD from Cornell University, and I graduated in 1963. Then I was a postdoctoral fellow, and in 1964, Feynman came to Cornell, and it was one of my greatest regrets that I could not hear him. But now with technology, you can see Feynman lectures, Einstein's lectures on YouTube. So that is the gift of God that we have, gift of the technology that we have. And so I will urge all the students to use this technology to learn and enjoy the Feynman lectures.
So Shruti Sharma asks an interesting question. The principle in general says the moment you observe the particle, the wave function collapses to give one particular measurement, also implying we can't ever predict what the state was before measurement. How did the question even arise that it would be a totally different state? And if you cannot actually measure it, how do you know it's a totally different state? So how do you know?
Like that if you have for sure a particular spin-up system, if an electron is in a spin-up state, and if I make a measurement of the x component of the spin angular momentum, then it will collapse. In this case, I know for sure that it was in the x up state, in the z up state, and it collapses either to the x up state or to the x down state. And so therefore, in some cases, you know the system, and then you can predict the probability of obtaining either the x up state or the x down state by passing through a Stern-Gerlach SGX cap. That is what they call. So something like that.
So there are lots of messages thanking you.
I'm glad everything went off well.
I mean, there's several. I'm not reading the names. Several messages are thank you, sir. You have valuable words, etc. I come to one question each you. It's wonderful lecture. I'm interested in the reference to the derivation of Bell's inequality explained here. So in case you'd like to give a reference.
Under my optics 7th edition gives just the derivation and the quantum mechanics book also. In both the books, I have given this derivation. I've given this derivation in the 7th edition of optics. I've given this.
So another person, Sharma, right? What is TETM modes in terms of photonic crystals?
TETM modes are in a planar waveguide. In a planar waveguide, you can rigorously have 2 independent solutions of the Maxwell's equations. Here, there is no quantum theory. Maxwell's equations, you solve that for, let us suppose, refractive index depending on n of x, and then you assume the refractive index depending only on the x direction. Then the solution split up into a set where there is Ey, Hx, 3 equations which involve Ey, Hx, and Hz, and 3 equations in which Ex, Hy, and Hz. So these 2, one describes the TE mode, one describes the TM, something like that.
So Subham Das, I think you have already answered this. Subham Das writes, can electron also be called an electromagnetic wave?
No, that is not possible.
Yeah. Then quantum mechanics, Vijay Sai writes very briefly on Hilbert space. I don't know what he means. I think He just writes very briefly on Hilbert space. You want to mention anything on Hilbert space?
If you have an n-dimensional, for example, I have a 3-dimensional space, 3 unit vectors, and I have x cap, y cap, z cap are representing the unit vectors. Now, if I consider the solution of the Schrodinger equation for the linear harmonic oscillator, then any wave function in the x space can be written as superposition of the eigenfunction of the linear harmonic oscillator problem. What are those eigenfunctions? N normalization constant, Hn of xi e to the power of minus half xi square. These are the eigenfunctions in the harmonic oscillator problem. So these form a complete set of orthonormal wave functions. Each wave function can be considered as a vector, and there are infinite orthogonal vectors. This constitutes a Hilbert space, an infinite dimensional vector space, where each vector is orthogonal to the other. So it's an imaginary 3-dimensional space I can imagine. But any function, any well-behaved function f of x can be expressed as a linear combination of these vectors. So each wave function, each ket can be thought of as a unit vector. And you expand an arbitrary ket as a linear combination of them. So these infinite number of orthonormal kets form a Hilbert space.
Okay, so Prithviraj Ganguly, does electromagnetic wave interact with charge?
Of course, you have an electromagnetic wave associated with that is an electric field and magnetic field, and if the charge is there, it will certainly experience a force. Certainly, it will experience. In all simple problem, of course it will.
Gaurav Shukla asks, I have a question about Fermat principle. Is there any example where light takes longer path instead of a shorter path?
Of course, I have given that in the 7th edition of my optics. I've given that, of course. In simple imaging by refracting surfaces, you can have a minimum time, maximum time, and a stationary time. Well, all rays take exactly the same amount of time. If you have a secant hyperbolic distribution of refractive index, this is used in waveguide theory, and you have where connecting the 2 points, there are infinite number of paths. This is true even when in a paraboloidal reflector, all rays come focus at the same point. Then all rays take the same amount of time.
So yes. One question by Archis Mukhopadhyay. Why does the wave, I think you've already answered, why does the wave function collapse upon observation? Is there any theory for this?
This is the axiom that I have learned. This is somewhat like an axiom.
I think one different type of question, Aniska Ranjan, why quantum mechanics is independent of temperature? I only understand the solution of the hydrogen atom problem. So I consider that temperature will come in. You see, in the hydrogen atom problem, if the one hydrogen atom is moving with a large velocity, then the center of mass is moving with a certain velocity that is represented as a plane wave. And then the internal dynamics is solved by solving the Schrodinger equation. So temperature is associated with motion. If you have millions of atoms, then it becomes a very, very difficult problem. So I think, most of the Shruti Sharma asked the same question you already answered. Shovik, you have derived the Schrodinger equation from the plane wave equation itself. Is there another way of proving it? The Schrodinger equation.
Schrodinger equation. Each book has its own way of arriving at the Schrodinger equation. If you read Feynman lectures, it is entirely different. Dirac's book, it is entirely different. Bohm's, what I have done is somewhat similar to what Bohm has done. But each book has his own way of getting at the Schrodinger equation. And If you read Dirac's book, it's entirely different. It's entirely different. So because there is no rigorous way of going to quantum mechanics from classical mechanics.
So somebody asked actually on that, how quantum probability is different from classical probability.
Oh,
Raj Ganguly.
I will give you a very simple example. Which we learned at the school level. I take a solid. Let us suppose it is uranium. Let us suppose it has 1 million atoms, 1 million nuclei. It is radioactive. Now, I say it has a half-life of, let us suppose, 1 day. That means half of the atoms will decay in and produce an alpha particle or something like that in 1 day. Now, which half? That no one can tell. That which atom will decay. Quantum mechanics allows us to calculate the lifetime from first principles. I have done that in my book, using WKB analysis. The rigorous calculations are difficult, but in principle possible. So I can calculate the lifetime, but the probability concept is, it is not tossing of the coin. It is something very much deeper than that. That there are 10,000 atoms, 5,000 will decay approximately. Which 5,000? No one can say. So and there lies the concept of probability associated with quantum mechanics. Here, if you flip a coin, if you know exactly the position of the coin, the air resistance and things like that, you can predict whether it will be head and tail or something like that.
Thank you.
But here you cannot predict. Even God does not.
Yes, I think just the clarification, sir. I think it is the difference between distinguishability and indistinguishability. Basically, that classical particles are distinguishable in some sense. I believe, sir. That probably answers or clarifies your answer. I would say. There is a final question I will take on effective mass of an electron. Somebody says we do not know what is an electron. Then how are you even able to know the effective mass of an electron?
You have the famous mass. I know of the electron through other measurements, and I know up to 10 decimal places. So I know the mass of the neutron also to 10 decimal. How do I know? There are experiments which determine the charge and the mass of the electron. Something like E by M, which was determined by Robert Millikan in 1911 or 14 or something like that. So there are methods of determining the mass, and it has a very well-defined mass. There is no doubt about it. Electron, proton, neutron, they all have a mass which is very accurately determined. But if you ask me what is the structure of the electron, I don't know. No one knows. Because how does it, because again it comes back to the same question. And this is what Feynman writes. The double hole experiment sums up the entire quantum mechanics.
That's right. I think this is the final question we'll take from the chat box. If two photons collide, what happens?
Photon scattering. I don't know.
Two photons collide.
Electron scattering. Electron scattering. If proton scattering, we have the Rutherford's modified form of Mother Rutherford. You can have a singlet state scattering, triplet state scattering, something like that. What is the force of interaction between two photons? I really don't know. I've never thought about it. But I know the force of interaction between a proton and an alpha particle, or proton scattering. I know that there are all kinds. At low energies, things are very easy to understand. It is approximately given by the Rutherford formula, but you have to take into account the fact that it can be both in the singlet state and in the triplets.
I think
but answer to the question as to photon scattering, I really don't. I am unable. Maybe someone else can.
Thank you. Thank you, sir. I think it has been really wonderful to have so many chat box questions. There are several. Thank you, sir, which I just did not read because it will take too long a time. But let me thank all those people who have interacted in the chat box. It has been wonderful from all of you. In fact, it's just, as you can see, there are so many thank you messages. So you can see this is one of the most popular evening lectures that I have ever attended. that I have ever attended. I will, yes, some more thank yous have come. Meanwhile, I should now actually go back to those others if they want to ask any question. I saw somebody had put a hand raised. In case he or she has already asked the question in the chat box, it is okay. But otherwise, anybody else who would now like to ask question?
I just would like to say it was a beautiful lecture. It was a beautiful lecture, especially in the end when you showed how the singlet state decouples. The quantum, for the first time, I think I have understood entanglement. It's always been difficult. So I think if that one illustration of yours was worth for me to attend the whole lecture. I want to thank you.
Oh,
thank you.
It doesn't mean that the rest of them are not important, but the rest of them were beautiful. Overall, it was a fantastic lecture. I'm going to buy myself a copy of this 7th edition of your book.
Yeah, I think Professor Ghatak, you summarized that by the double-slit experiment of the Feynman's lecture. I think that really is great. So people should just go back and look at that again.
Yeah. No, listen to the Feynman lecture.
Feynman lecture.
If I've been able to persuade the students,
I think it's always wonderful to keep listening to his lectures.
That is true. That is true. And his lecture on gravitation. That is also.
So, anybody else would like to ask questions before I hand it over to Professor Panigrahi?
No, that's enough.
Okay, I know it has been, but you can see, Professor Ghatak, that how popular was your lecture. And I think
I'm so glad there is so much of interest. There is so much,
it is just wonderful.
It brings me, you see, I am very, I should not say this in front of the younger generation. I am now very concerned that getting good jobs is becoming very difficult. So how will the younger generation get motivated to learn physics and mathematics and basic subjects? All our bright students are going for MBA, which is all right. And they are getting phenomenal jobs and salaries. And who will teach physics? Who will teach this thing? So this is a worry. You see, when I came back from USA in 1964, the salaries were very low. But getting a job was not a problem. Getting a job was in a good institution was not a problem. Today, it has become a problem. I do not want to say this in front of the younger generation, but unfortunately, you have to put the blame on all of us, all the senior people sitting here, that why didn't we think ahead? And even now, things are becoming a little more difficult. But teaching, you see, there is one thing that I would like to tell all the students, that I am now 83, almost 83, 82 plus. But the very fact that I keep myself active, give lectures, it is because I'm in a subject which interests students and things like that. So if you join academics, you will never retire. That is what I can tell you. And
that's the beauty. That's the beauty. That's the beauty. So, I mean, thank you all for this chat box. Since I have taken all chat box questions, there are 2 more which have come. So, but please do not, we cannot take any more. I'm requesting all of you because it's a long lecture and long interaction session. Somebody has written, tell us about how to learn science language observing nature. The language of science, I think it's a very, I thought it's a different kind of.
What do you mean language of science? What do you, I don't know. You read good books and listen to good videos. And today, you see, the option is with you, the younger generation, that in YouTube, you get brilliant lectures, brilliant discussions, and you get very bad things also, The choice is now within you. If you want, today, even in a remote area of India or anywhere in the world, if you have access to the internet, and thanks to our technology in India, we have access to internet almost everywhere, knowledge is almost free. And therefore, you read good articles, you listen to good lectures, you listen to good music, everything is available, everything is free. Everything is free. So
Thank you, Professor Ghatak. I think the final question, can you put electromagnetic field in the category of fluid? Because most of the properties are matching.
No. I don't think so. Electromagnetic wave passes through vacuum, and how can you? A fluid flow will be described by Navier-Stokes equation or something like that. And electromagnetic wave, classical electromagnetic wave, I will describe it as a Maxwell's equation. So these two are completely different. So how can I'm
Yeah, thank you, sir. I think it's I mean, I don't have to say how good it was, because it's the proof is in the pudding. I mean, everybody would agree that it was probably the best evening lecture, at least one of the very best evening lectures that I have ever attended.
Oh, thank you.
So it was really wonderful, and
nice
thank you very much from the bottom of my heart for giving such a wonderful lecture, and thank all the participants. You know, it went more than 200 and around 220 or more at the peak, and that's really wonderful to see so many participants and who have interacted very enthusiastically. Thanks to all of them. Before you completely,
what I am admiring most is the following. Let me tell you.
Yes.
What I admire most is that the director of an institute is sitting there listening to it. So that is very, you have set a very good example.
No,
I'm very happy and proud.
I learned a lot.
Photonics, do you agree with me?
I learned a lot. You know, it's how to speak lucidly, and a lot of concepts. Yeah, it's very good to hear. I have great interest in quantum mechanics also, so I think it was good. I actually am a professionally quantum chemist. So I think it was good to listen to you. And just like Professor Satyamurthy is. So I will now, thanking you, I will hand over to Professor Panigrahi to close the session. Thank you, Professor Ghatak.
Thank you.
Actually, I don't have anything more to add. Wonderful talk. And Professor Ghatak will work out this entanglement proof in one of our tutorials, because I am seeing it for myself for the first time. I was not aware about this. Thank you. Thank you, Professor Pal, and thank you, Professor Satyamurthy. Thanks. Yeah.
Thank you, Professor Ghatak, Professor Satyamurthy, and all the Professor Panigrahi and all others who are here. Thank you.
Thank you.
Thank you.